Hello, everybody. Welcome to today's web seminar. Today, we're going to be discussing calculating rigid body properties from FRF measurements. If you don't recognize my voice, my name is Kevin Grenier. I work in the customer services team in the Detroit area. So today, we're going to show a seminar that will show how to use FRF measurements to calculate the rigid properties of a structure, including its center of gravity, the moments of inertia, the direction of the principal axes of inertia, 6 rigid body modes, and you can also verify the mass. You tell us the mass during it, but if you look at the mass of the rigid body modes, it kind of gives you an indirect calculation of the mass as well. So why are inertia properties needed? Verification of the center of gravity and the moments of inertia. So perhaps you have a simulation model and you want to either see if it's correct or perhaps update it based on physical testing. You could do that by getting the center of gravity, moments of inertia with this technique. You can use that for input to different simulation models. I put a couple of examples here like SimCenter 3D, Atoms, Elestina. You can use it for kinematic and dynamic prediction. So multi-body dynamics, for example. If you're doing coupling between finite element models and test, you could use this in modal coupling. So there's a tool called modal coupling or modal synthesis, where you combine different modes together to get the set of system modes. And if you want to do that, it's important to have a complete modal model. And that complete modal model needs to have the rigid body modes, the flexible modes you test in the modal analysis, and then the upper residual terms, the static compensation modes. So a complete modal model has those 3 different areas. So flexible modes, you can do an impact hammer test or a shaker test. Take the data in the modal analysis or Polymax modal analysis and get the flexible modes. Sometimes during testing, you might find 1 or 2 of the rigid body modes, maybe 3 if you're lucky. This tool is going to give you all 6 rigid body modes. So you can use a rigid body calculator to calculate the 6 rigid body modes, 3 for translation and 3 for rotation. You can also use this tool to get the upper residual terms. And then you want to create a complete mode set that has all 3 of these, the rigid modes, the flexible modes you tested, and the effects of the modes above your frequency range of interest, the upper residual terms. And we can calculate all 3 of these inside TestLab. So how to determine the initial inertia properties? Typical modal test with a hammer excitation, at least 6 reference locations. So normally when you do a modal test, you're probably going to impact in 1 location or 2 locations. 2 is nice because you can get repeated roots if you have 2 resonances at the same frequency. Here you could set up your modal test and just get a couple of additional excitation and use that same modal data to get the rigid body properties. And you'll see in the software that if you have more than 6, it's nice. But in order for the tool to work, you really need to have at least 6 excitation locations. Here the picture is showing a shaker. In practice, that's not commonly done. It's kind of a pain in the butt to move a shaker to 6 separate locations. So normally we would use a hammer for this type of a test. And then as far as response locations, you need at least 8 triax accelerometer locations. So here we say 8 to 12. If you're doing a complete modal test, maybe you have all of the accelerometers on at one time and then impact in at least 6 locations. If you don't have enough accels to put them all on at once, you could put dummy masses on, and that way you have maybe 1/3 of the points are tested and 2/3 have dummy masses. You can hit at all 6 points, then move the accels and the dummy masses, hit at 6 points, and then do your 3rd move and hit at 6 points. That way you'd have a complete modal test with 6 references and all of your response locations measured. So here, no extra equipment's needed. Most labs have an impact hammer and an accelerometer. Limited measurement effort if you're not going to do a whole modal test. All you need is at least 8 triax locations and 6 impact locations. You only need to suspend it once, as opposed to a pendulum test where you have to suspend it multiple times. And it's highly accurate alternative to a conventional pendulum test. So the left side is what we're proposing in TestLab to use a rigid body calculator to get the rigid body properties. Historically, we've done pendulum tests. So you need to hang your test object to swing about multiple axes and then measure the amount of time it takes to swing, and then figure out the center of gravity for that particular hanging of the test object. And using the center of gravity locations, the known mass, and the swing time, you can calculate the moments of inertia. So this is a little time consuming to hang it multiple times, calculate the swing times, and it requires multiple swings. Rigid body calculator in test lab, we can synthesize the rigid body modes based on FRF measurements. Input is going to be the geometry. And here I have accurate. We're going to use your geometry to calculate moments and use that to calculate the moments of inertia. So you want to make sure the geometry is as accurate as possible. So perhaps getting it from CAE or getting it from a CAD model or measuring it very, very accurately. You want the FRF data to be as accurate as possible. So you want to make sure that you have it properly calibrated for the hammer and the Excel. You also want to make sure that it's properly ranged. So you want to range at every single location. And you want to make sure that you have the mass of the object measured accurately. So here we want to be a little bit careful measuring accurate FRFs because we're going to use a portion of the FRF data you don't normally look at in order to do this calculation. So we're going to be looking at an area called the mass line between the rigid body modes and the flexible modes. It is going to have very low amplitude. And because of that, it's really important to range every time you rove your Excels or rove your hammer location, because we want that low amplitude to be measured as accurately as possible. We want to try to move it away from the noise floor. The output is going to be inertial properties. So we're going to get the center of gravity, the mass, if you look at the mass on the rigid body modes to verify it, the moments of inertia, and the directions of the principal axes of inertia. We also provide 3 rigid body modes that are translation and 3 rigid body modes that are rotational. Yeah, we like to use dummy masses to compensate for any mass loading effects. So if I put an accelerometer on a structure and put a second accelerometer next to it, and if the FRF shifts, then you have mass loading. So one way to compensate for that is to test with all of the accelerometers on at once, and then remove the weight of the mass when we do modification prediction. If you're not rich enough to have all those accels, you would use dummy masses that weigh the same as your accels, and then swap the dummy masses with the accels as you rove your accels. And then after you calculate the modes, you would use modification prediction to remove the weight of the accelerometers or the weight of the dummy masses. More important for light structures. So here's an example of a single degree of freedom system. So we can approximate the structure as a single degree of freedom. So here I have a resonance. And the resonance we're talking about here is actually the first rigid body mode, or one of the rigid body modes, where it's bouncing on a suspension or on bungees or on springs. And the left side of the peak is the stiffness controlled region. And where it hits 0 hertz is what we call the static stiffness value. The right side of the peak we call the mass controlled region. And we're going to be calculating these rigid body properties in the very flat line between your rigid body modes of your structure and the first flexible mode. So we're going to calculate the rigid body modes inside this region here. So the line above that FRF peak is called the mass line. So the line above the rigid body mode you're testing is called the mass line. It's relatively flat between the rigid body modes and the first flexible mode. And there's kind of fancy math here, but basically this line approaches a constant value, and we can use that information to calculate these rigid body properties. Test setup, weigh the object to get the mass. Suspend it in free conditions for all 6 rigid body modes with very low stiffness. That's really important. You want to make sure when you're hanging their object, and we're hanging a powertrain here, you want to make sure that you're not constraining it so it has trouble bouncing in any of the 3 directions or rotating in any of the 3 directions. And you could see perhaps if I had a horizontal bungee, I could possibly be constraining it about a yaw mode here, or maybe if I had a bungee that was too stiff vertically going to the top and the floor, perhaps I'd be constraining that pitch mode. So you want to make sure when you pick your bungee locations, you're not constraining it so it can't bounce about X, Y, or Z. And you want to make sure you're not constraining it so it doesn't rotate about X, Y, or Z as well. You want to make sure it's free to move, translate, and rotate in all 6 degrees of freedom. Create an accurate geometry in global and local coordinate systems. Measure the FRF matrix, preferably with a hammer with a very soft tip. So you don't want to use a stiff tip because that's going to excite all of your higher resonances as well. You want to use a really soft tip. So predominantly the rigid body modes and the first couple of resonant modes are being excited. You need to have at least one resonance mode measured. Okay, so make sure that your bandwidth is high enough that you capture at least the first flexible mode so you know where it's at. And then you need at least 8 tri-X response locations. So 24 response points, 8 times 3. More helps. And then at least 6 inputs. And again, more helps. You're going to see when I show you the software, I can check the correlation of all of my reference locations. And if 1 or 2 of them are low, I can get rid of them. And if I have more than 6, I have that option. Same thing with the response locations. I can check the correlation of all my response locations. And if some of them are low, I can get rid of them if I have more than 8 tri-X's. So it helps to have more response points, and it helps to have more reference points if you can. And if I look here, this is a region where we're calculating the rigid body modes. So here I probably have too stiff of a tip, and I may be measuring out too high in frequency because I'm exciting all of these flexible modes. And we're going to calculate the rigid body properties right here. Here I've got my rigid body modes, real low frequency, I can barely see them. And then here I would have my mass line. So when I teach this class, I put this slide together on some practical considerations. So again, support the structure free, and make sure that all of your 6 rigid body modes are free to move. So don't constrain it in any degree of freedom for translation or rotation. Again, measure the geometry as accurately as possible. Calibrate the transducers, the accelerometers. If you have long cables, that might be important because that may change the sensitivity. If you haven't had your hammer calibrated in a while, or maybe the cable's really long, you want to calibrate the hammer as well. So we can calibrate the accelerometers. A lot of people are familiar with that. We could also do a relative calibration in the software, and that would calibrate your hammer using a known accelerometer input. Aim for high measurement accuracy in the lower frequency range. So frequency resolution should be pretty tight, very low frequency resolution. You don't want to have a delta F of 1 Hertz or 2 Hertz because your rigid body modes are probably within that frequency resolution. Perform the modal test using a single reference excitation. This just means I'm not going to put 6 shakers on it at once usually. If I'm going to put 6 shakers on it, I'm probably adding 6 constraints. So it's not going to be free to rotate about those 6 degrees of freedom. So usually we use a hammer, and we route that hammer to at least 6 impact locations. Use a frequency range of excited that includes at least the first flexible mode. So you want to know where that first flexible mode is. Because the frequency range of interest is low, use an appropriate hammer and hammer tip. So use as soft of a tip as you can, and use an accelerometer that measures low frequency, or perhaps even a DC Excel if you have them. But usually that's not needed. Usually a good ICP Excel usually will measure down to 0.5 or 1 Hertz pretty well. Typically 6 different excitations, so you need at least 6 impact locations. And when you choose those impact locations, you want to make sure you choose them such that X, Y, and Z are properly excited for translation as well as rotation. So I probably don't want to pick impact locations along the center line because that's not going to excite one of the rotational rigid body modes. So you want to probably pick maybe boundaries of your test object and pick your X, Y, Z impacts along the boundaries such that all 3 translation modes are excited as well as the 3 rotational modes as well. So we'll avoid the center line. And then between 8 and 12 response points in 3 directions are required. Responses should be spread over the structure. Try to place on a box outlining the structure. So we used to have a coworker that worked with us, and he was real big on putting the accelerometers on the outlier, or if you can imagine a box going around your test object, you want to have your accelerometers on the outside of that box. That's going to avoid any center lines, for example. It is going to have the largest displacements as things start to translate and spin. Try to think about putting those response locations on the outer parts of your structure, as if you draw in a box that contained the whole thing. Validate the consistency of the measured FRFs, such as correct calibration, correct direction, and sign before start the rigid body calculation. So there's some things you can do. If I look at the data in modal validation, we can start to look at modal complexity, and you want to make sure some things are true. You want to make sure that the mass sensitivity is negative, meaning that if I were to add mass, the frequency would go down. If your mass sensitivity is positive, some of the directions are probably wrong, and then you're going to get funny results in rigid body calculator. If your modes are highly complex, so if they've got high phase scatter, and if they're highly nonlinear, this tool is probably not going to work that well. So again, do some modal validation checks and make sure mass sensitivity is proper, and make sure that the modes are fairly collinear. There's also a newer tool. There's a display called the function heat map, and you can use that to put all of your FRFs in it and make sure that the phase is correct. So there should be an FAQ on this community site that using that display, and you can quickly see if some of the directions on the FRFs are incorrect. And that would be very important before you do rigid body calculator. Choose the most appropriate mass line method. So I'm going to talk about 3 different methods. So the one you choose is going to be depending on your data. And then synthesize the rigid body modes with a low frequency. Specify the frequency you want. Specify the damping value you want. And then look at them. And if I'm calculating 6 rigid body modes, they should look like 6 rigid body modes. So animate them and make sure all the points move together for all the translational and all the rotational modes. So just some test considerations or things to be careful of. So here is a typical FRF. So here at low frequency, I have the rigid body mode. Here is the mass line between the rigid body modes and the first flexible mode. And we're going to calculate the rigid body properties in this frequency band. And you have control via a double X cursor what frequencies you're using to calculate the rigid body properties. So I would normally put all the FRFs in this display and choose a band that has the least amount of noise and where the mass line is flat, provided you have enough spectral lines to do the calculation. And I'll show you that in the software. When you pick the double X cursor, it's going to tell you how many spectral lines are in this frequency band. And we're going to do the calculations via a least squared fit across all of those spectral lines. So it helps to have more spectral lines here, provided the mass line is flat and free of noise. And then these are the 3 methods: unchanged FRFs. Rigid body modes and first flexible modes are sufficiently spaced, and we have a nice clean mass line. So if that's true, and that's true in this example, I would choose the unchanged FRFs method. That's always going to be my default go-to method, provided I have a nice clean mass line. If I don't have a nice clean mass line, then I would do one of the other methods. Corrected FRFs, rigid body modes and first deformation modes are not sufficiently spaced. So there's an example here. Estimate the first set of flexible modes from the measured FRFs, and then correct the FRF by subtraction contribution. So basically, corrected FRF means I'm going to calculate the first couple of flexible modes, store them, synthesize the FRFs from those flexible modes, and subtract it. So basically, I'm going to use my modal data to synthesize this peak and subtract it, so you end up with a flat mass line by removing that part using a synthesized FRFs. That's the corrected FRF method. So we're modifying the FRFs using the FRF synthesis from the modes you have calculated. So there you not only need to have 1 or 2 flexible modes, you need to calculate the mode shapes as well. The third method is a lower residual. And then rather than adjusting the FRFs using the synthesized FRFs, we're going to use a lower residual term on your flexible mode calculation to adjust the FRFs. So there the measure FRFs aren't adequate in the frequency range of interest. Lower residuals represent the influence of the modes below the deformation modes, and therefore representative of the rigid body modes. So we're going to use the lower residual terms in that third method. So those are the 3 methods we're going to have. The first one doesn't change the FRFs at all. The second one modifies the FRFs using the synthesized FRFs. And the third one uses a lower residual term on mode calculation to calculate the rigid body properties. And here you can see it's very noisy. I don't have much faith in these low frequency measurements at all. So I'm going to use a lower residual term instead. Here in the second one, I do have good measurements of the low frequency. I just have to compensate and remove the effects of the first flexible modes. Where is it? So we have to go to add-ins and we have to turn on the rigid body calculator, and it'll warn you it needs a prereq of modal analysis. So we use part of the modal analysis capability with this tool. So we need the modal analysis add-in as well as the rigid body calculator add-in. We're going to need both. We're going to use modal data selection to pick and choose the FRFs we're going to use. And then the rest of the work will be done on the modal rigid body calculator worksheet. And that has two minor worksheets, a data selection worksheet and a calculate worksheet. And I'm going to show this in the software too. So here's the data selection worksheet. Here's all the FRFs I'm going to use. I've got the references or the impact locations along the top as columns. I've got my responses or my accelerometer locations as rows. And the plus or minus tells you if it's positive or negative. Then down below, I can display the selected function, show it on the geometry, and show the sum block. Here in point 3, I can pick one of the 3 methods. Here we're on unchanged. Point 4, I can check to see if I've got enough data, and I can go to logging to see some additional information. So check is orange, minimum of 24 outputs recommended, and we only have 18. Okay, so that's telling me that I only have 6 tri-X locations instead of 8. And it's warning me with an orange color that I should have a couple of more Excel locations, but it's still going to do the calculation. If it were red, it wouldn't do the calculation. So if you're so far from the recommended settings or the recommended amount of data, it won't let you do the calculations. And then I'll talk about this, but here we can look at the correlation. It will show you the lowest correlation, highest correlation, and the average correlation. And you'll do that for all of the references. That is the columns. It will also do it for all of the responses, and that's the rows in this table. So here you can pick columns or rows, hit list, and it'll show the columns. It'll show the correlation here for either the columns or the rows. Columns are the references and rows are the responses. So here we can see the FRFs. We can calculate the sum block, select the band with a double X cursor, 3 mass line methods, unchanged FRF, corrected FRFs, and lower residual. And then we can validate the FRFs with rigid body correlation. Here we can calculate the rigid body correlation for columns or rows. ODS animation at the selected frequency band. So here I can pick a column and display and animate that. And then we've got some coloring and text feedback, whether it's green, orange, or red. And then the correlation numbers here, these correlation numbers represent, for this particular reference, how much of the response is going to look like a rigid body motion. And we do that for each of the references and each of the responses. And that number tells you what percentage does it look like a rigid body motion. So 100% means it's 100% rigid body motion. As that number gets less, it means it's not rigid body motion. So all the points aren't moving together. And then we move to the calculate worksheet. One, we have to type in the mass of the object. You can tell it to create a node at the center of gravity and give it a name. By default, it's called COG. I can hit calculate. I can tell it the frequency I want to put the rigid body modes at. I can give it a damping I want to save with the rigid body modes. I can tell it a degree of freedom mask, and I can give it a processing name. And when I hit calculate, it calculates the 6 rigid body modes, and it populates the rigid body properties in the upper right corner. Okay, so here it's kind of the same thing. It's going to give you the coordinates of the center of gravity. So here's the coordinates of the center of gravity. Moments and products of inertia about a reference. Here our reference we chose is 0, 0, 0. So in this case, the reference and the origin are the same, but it doesn't have to be. I could go under advanced and I can tell it whatever reference I want. And then we can calculate the moments and products of inertia about that reference instead of the CG or instead of the origin. And we also give you the principal moments of inertia in the direction. So here's the principal axis down here. You tell us to use to define frequency and damping for the rigid body mode, so you have to type that in. We synthesize the rigid body modes, and then we want to display them and make sure that the motion looks like a rigid body mode. So make sure all the points move together. And then if you turn on the nodes, you can see the CG. And if you know where it's at, it should be close to the origin. Here I have a brake rotor, so I know it's symmetric, so I can expect where the center of gravity is going to be, at least in this XY plane. And then we calculate the rigid body as a least squared solution over all of the response locations. Also a least squared solution over the frequency band, all those spectral lines. And we validate it by animating the rigid body modes. And then again, we give you these same results. Larger screenshot of what you have to populate. There's some additional settings under this advanced button. And then you can look at the center of gravity. If you turn on the node and the Euler angles, you're going to see the directions of the principal axes. Here it looks like we've got the origin turned on as well. So the right picture is the origin, and the left one is the node at the center of gravity and its Euler angles. So after you calculate the rigid body properties, you want to highlight this table and copy to Excel or copy to Word so you have a copy of it. So if you want this information for future use, copy and store it, save it to Excel. If you want, you could attach that to the documentation worksheet to keep it as part of the project, or just make sure you have it external somewhere in a file. Or you would have to go in and recalculate these. So here I have a brake rotor. We use this in the modal class quite a bit. And then under modal data selection, looks like I started playing with it. Let me go back to my default. Okay, so I have 23 references and 18 responses. So we basically impacted at 23 different locations, and we had 6 triaxes on the structure. So we should have had a couple more. So here I've included all the data. So you bring the data into modal data selection, and then we go right to modal rigid body property. And then I can see my 2 cursors here, and I can see I'm going to calculate my rigid body properties within this part of the mass line. So down here are my rigid body modes. Up here is my first flexible mode, and then this is the mass line. And I can see with these 2 cursor locations, I have 497 spectral lines. So that means I can do a least squared calculation over all 497 of those. So it helps to have more of those to get a nice solution. But if I wanted a smaller one, I can just come down, pick a smaller range, and now I have 159. And then if I wanted to look at if this is nice and clean, that looks pretty clean, that looks pretty clean. That has some noise here on the green curve. If I highlight all the data, it takes a while. And then I can see some of these measurements have quite a bit of noise. And maybe I want to retake them or maybe exclude them. But I can move these cursors around, and you want to try to get a nice flat part of the mass line, avoiding the rigid body modes and avoiding stiffness line on this first flexible mode. So let's say I'm not going to do any modification to the data. I'm just going to do the unchanged FRF method. If I look status here, I can check again. And it says minimum of 24 outputs, recommended 18. And if I look at the logging here, it gives you a little bit more information. Minimum of 24 outputs, we only have 18. So we had 6 triax locations and we should have had 8. Rigid body correlation for inputs, 92%. So the references have a little bit of a low overall correlation, and the responses have a pretty good 94.7% correlation. So it gives you a nice table if you have enough inputs, if you have enough outputs, and what the correlation is. But I'm going to leave that as is for now. Go to calculate. I'm going to have the mass. I'm going to call it unchanged FRF for my node name, unchanged FRF for my mode set. Frequency is going to be at 1. Damping is going to be at 0.1. I'm going to store the modes at every degree of freedom. And that's important because I only have 8 triaxes measured, but I'm going to write the rigid body mode at every single node on the structure. That's what the asterisk means. Okay, so it's not just going to store the rigid body mode on my 8 response locations. It's going to put, my 6 response locations, it's going to store the result everywhere because I'm using an asterisk for a degree of freedom mask. Under advanced here, I could pick a reference that was something other than the origin if you want. So that's where you would pick a different reference. And then I can hit calculate. Takes a little bit. I have a lot of FRFs. It's a 23 by 18 matrix. And then I can animate these rigid body modes. And you want to make sure, I go to an isometric view, make sure there's a bounce mode. Okay, so there's translation. Okay, there's another translation. There's a rotation about Z, rotation about Y, it looks like, rotation about X. Okay, so I have 6 rigid body modes. They look clean. I can see here my origin is 0. I can see the coordinates of the center of gravity. I can see the moments of inertia about the origin, which is my reference. Moments of inertia about the center of gravity. Principal moments of inertia. I can see the principal axes. So this table represents the axes. And the rotation about the reference. So this is the information you get. If you want, you can copy and paste this to Excel or whatever you want. That's the first method. If I go into data selection, and now I pick corrected FRF, and now I have to pick a processing. So you have to have a processing, and I have 2 here. I have one with 2 flexible modes and one with 3 flexible modes. So I pick a processing set, and then I go back to calculate. Which one did I pick? Corrected FRF. So I'll call this corrected FRF. Okay, so I'm going to have the center of gravity called center of gravity corrected FRF, and the mode set called something very similar. So it's done. So if I zoom in now, these two got really, really close. You can see how close it is to the origin, and these two are basically almost on top of each other. So one of them is using the FRFs as I gave them with the unchanged FRF method. The other one is looking at the 2 modes I've calculated, synthesized the FRFs for those 2 modes, subtracted the synthesized FRF from my original FRF to give myself a nice flat mass line, and then doing the calculations over that same double X range I specified. So from 129 to 377 Hertz with 497 spectral lines. If I look at geometry here, and if I look at my nodes, I have to pick the geometry because they're not saved in a component. And you can see that they are very, very similar, except this Euler angle is a little bit different. So that's the only difference, is that it's rotated a little bit. So if I yeah, you can see there's a little bit of a difference. It's hard to see. Now, so let's try the third method. So now if I go to modal rigid body properties, go back to data, and switch to the lower residual method. So this would be used if you don't have a good mass line and the FRFs at low frequency are fairly noisy as well. And then we're not going to use that information at all. We're going to use the lower residual term from the mode set. And again, you have to go and pick one of your modes. I'm going to use the same mode set with 2 flexible modes in it. Go to calculate, and now I call it lower residual. And I'll call the mode set something very similar. And then if I look at that one's actually a little off. So you can see it's over here. So if I look at the geometry and look at my nodes again and look at the geometry, So that's this one here. So you can see it's a little bit different, and the angle is quite a bit different as well. And part of that is it's really hard to find these modes. This is not a great data set for doing this tool. I think they have too many references. We have 23 references, and they only have 6 triax locations. So I only have 18 response points. And if I look at the stabilization diagram, when I teach this class, I don't normally show that second and third method because I couldn't get good modes. So I spent a lot of time with this data yesterday trying to get at least the first couple flexible modes. And you can see here, I had to really crank up the model size. And the reason is the stabilization diagram gets noisy when you have so many references. So here I have 23 references, and that stabilization diagram really gets confused with that many references. Part of the reason we came out with maximum likelihood modal model, the MLMN modal estimator, that might improve the data a little bit more, because that's really helpful when you have stabilization diagrams with lots of references. I should have turned it down from 600 model size before I came to this worksheet, but it's almost done. So you can see the stabilization diagram. And I've got a couple of modes here. Looks like I have 1, 2, 3, and I had to really look hard to find these first couple flexible modes. And that's what I used in that second and third method. And that lower residual method, I think it got fairly poor results, but the corrected FRF measurements got real good results. So if I look again, so there's the 2 degrees of freedom, one with the corrected FRF method and one with the unchanged FRF method, and they got really similar results. And the one over here is the outlier that used a lower residual. I didn't get good results with that technique with this particular data set. Okay, so let's say I wanted to improve even more. Okay, so let's say either the corrected FRF, it seems to be getting me good results, or the unchanged FRF is getting me good results. So what else can we do? So basically, let's calculate this correlation of my columns. And then I can see across this, for each one of these references, I can see the lowest correlation, the highest correlation, and the average correlation. So if I go through this list, this is the worst one here, upper plate 23Y. So that has got a correlation of 91 as the lowest and an average of 92. But we'll see, we'll check that logging again once I get rid of this. So if I wanted to get rid of this reference, upper plate 23Y, I'd go back to modal data selection, look for upper plate 23Y, right there, right click and say exclude. Older versions of the software, you can't right click and exclude. If you don't see these colors, you'll have an exclude down below the table. So this changed, I forget if it's Rev 18 or 19, but now we changed and it's colored, and you don't have the include and exclude below the table. But when you right click on a column or row, you can exclude or exclude from stabilization. So here I've excluded it from everything, so it's turned red. If I only excluded it from stabilization, it would have turned orange. So now I go back to modal rigid body property, and then I can check these again. And then after it's done, I'm going to check the logging and see if it improved. And I don't remember, I think it was like 92 before. I think when I checked this before with this particular unchanged FRF method, I think the responses or the outputs was orange. I'm sorry, it must have been for the inputs. The inputs was orange and it was 92% or something like that. So now I've improved the correlation. All of my references are acting 98% like a rigid body mode, and all of my responses are acting almost 99% like a rigid body mode. So now if I go back to calculate, and let's call this unchanged FRF 2. Well, let me do FRF 2. By just keeping everything for bookkeeping, giving it different names so it doesn't replace the node. Hit calculate. See, now it's even getting closer to the origin. Okay, so it's moving towards the origin. These are the first two, and then this was the last one I just calculated. So I could repeat that. So if I go back to data selection, I could go and see if there's any other references I want to get rid of. So here's 97. I already got rid of this one, 97. Okay, so there's none really I really want to get rid of. But if I wanted to, I could go back to modal data selection, pick another column, exclude it, then I would have two excluded. Then I would go back to rigid body properties and then check and log if I wanted to check the global correlation value, or just go over to calculate and calculate. So now what if we wanted to get rid of a response? So instead of list rigid body correlation by columns, I'm going to do it by rows and hit list. So here's rigid body by rows. So here's 98, 99. So 98.2. So 98.2 is probably the worst one I have. So if I wanted to get rid of one of those, I would go back to modal data selection. And then I would select the row I want to get rid of, right click and say exclude. And that would get rid of one of the response directions. So they give us some tools by looking at these global correlation values. And again, this is percent. It's acting like a rigid body for the references and the responses as inputs and outputs. And I can see it per reference or per row by using the table here, by listing the correlation by either columns or rows and clicking list. And then here I kind of know where the center of gravity is at, so I at least can tell in the XY plane when it's getting good. And I can compare that to if I go to view extensions, I can turn on the origin. And as you zoom in, you can see how close you are to the origin. Or I can go to geometry here, go to nodes, highlight the geometry, and then I see the nodes I'm creating exist at the geometry level and they're not tied to a component. Here's another example we have. And here we can see we've got 3 of these vertical beams on the right side and only 2 on the left. So you'd expect it to be a little bit off-centered. So if I look at one of these views here, you can see it's a little bit to the right rather than being exactly in the center. And I calculated it a couple of different ways. So these are the 3 different methods using this other data set. So I checked it in a different data set as well. And then we've also tested it on an exhaust. Let me show this modal validation tool. So if I go to modal validation, I can find my flexible modes here. So flexible 2 modes. So I can add those to the workspace. I can find my rigid body modes. So maybe unchanged FRF2. Bring the rigid body modes to the workspace, and then create a new mode set, call it combined, and hit create. Okay. And then if I want, I can go to the static compensation. Frequency factor is 10, so that's going to take the highest frequency in the mode set and apply a factor of 10 to it. These are the 2 different scaling methods, singular value decomposition or scaling. And then I can calculate. So it added those. And now I can call this combined final. And now it's got the rigid body modes, the flexible modes, and the static compensation modes. That's how we do that last step. Let me go back to the slides. So we did a validation on this type of a structure. We got very good results. As the number of references goes up or the number of responses goes up, the rigid body correlation goes up and the rigid body calculation accuracy goes up. So like Charles asks, it helps if you have more references than you need. So try to get more than 6. And it helps if you have more responses than you need. So try to use more than 8 triaxes. Last slide, I found this kind of a neat guy that was demonstrating how to use a built-from-their pendulum. So he built one out of a 2x4 and walks through all the calculations on getting the pendulum swing times and calculating the rigid body properties that way. And I found a more technical explanation as well if you want some reading material. All right, well, everybody, thank you very much for your time. Thanks for your interest. Let me know if you have any questions.